From Earth, Uranus appears as a distant pale blue point of light, barely visible to the unaided eye even on the darkest nights, requiring a telescope to reveal its character as a planet rather than a star. The journey outward from our world crosses nearly 3 billion kilometers of space, passing the orbits of Mars and the asteroid belt, sweeping past Jupiter and Saturn, reaching finally into the outer solar system where sunlight arrives weak and cold. At this distance, the sun appears merely as the brightest star in the sky, rather than the overwhelming disk that dominates our own sky, providing only about 1/400th the light that reaches Earth. The ice giant hangs in the darkness, a world tilted on its side, with rings and moons circling around its poles rather than its equator, creating a system unlike any other in the solar system. 28 moons orbit this sideways planet, each one a world with its own characteristics and history. And tonight, we move among them slowly, visiting each major moon to understand what makes it distinct. Some of these moons circle close to the planet, completing orbits in hours or days, while others wander far out on paths that take years to complete. And together, they form a family of ice worlds, orbiting in configurations that reveal the system's formation and evolution. The approach begins with the innermost of the 5 major moons, a small world that appears unremarkable from a distance, but reveals itself upon closer inspection as perhaps the strangest moon in the entire solar system. We descend toward its surface, where impossible cliffs drop through vacuum, and frozen terrain shows patterns that make no geological sense. And we settle here to explore this bizarre world thoroughly, before continuing outward through the system. You are listening to the Drowsy Astronaut, where we explore the cosmos slowly and without hurry, settling into one place at a time to understand it completely before moving on. Tonight, we journey through the moons of Uranus, visiting 28 worlds that orbit a planet tilted on its side, far out in the cold darkness of the outer solar system. If you find yourself comfortable wherever you are listening from, feel free to leave a comment about which moon intrigues you most, or what draws you to these distant ice worlds at the end of your day. The like and subscribe options are there as well, if this kind of patient, cosmic exploration brings you some calm during these hard times. Just an invitation to return whenever you need something vast and real, and quietly fascinating to think about as sleep approaches. The moon we approach now bears the name Miranda, smallest of Uranus's 5 major satellites, a world only 470 kilometers across, roughly 1/7 the diameter of our own moon. The surface comes into view as we descend, and immediately something appears wrong with the geology, as if different pieces of entirely separate worlds were fitted together, without regard for how terrain types should transition naturally. 3 distinct regions show themselves clearly from orbit, each one internally consistent, but bearing no relationship to the regions adjacent to it, creating boundaries as sharp as if someone drew lines on a map and assigned different characteristics to each section. The oldest terrain shows heavy cratering from billions of years of impacts. The scars accumulated over geological time, creating a landscape marked by circular depressions overlapping each other in patterns that speak of immense age. This ancient surface appears dark grey, the ice mixed with rocky material, or possibly organic compounds that give it a muted colour, the craters showing little sign of erosion or modification since they formed. The surface here resembles what we might expect from a small icy moon, the bombardment history written clearly in the density and distribution of impact scars. Nothing about this cratered terrain seems particularly unusual until we notice that it ends abruptly at a boundary where completely different terrain begins. The grooved regions, called coronae, show parallel ridges and valleys cutting across the surface in organized patterns that indicate tectonic forces stretched and compressed. The ice crust. 3 major coronae exist on Miranda, bearing Shakespearean names like the moon itself, Arden Corona, Inverness Corona, and Elsinore Corona, each one an oval region perhaps 200 kilometers across. The grooves run parallel to each other, with spacing that suggests regular processes rather than random fracturing. The ridges rising perhaps a few hundred meters above the valley floors. The material in the coronae appears brighter than the cratered terrain, suggesting younger ice, less darkened by radiation and micrometeorite impacts. And the sharp boundaries between cratered and grooved regions create the impression that these are pieces of different moons, somehow assembled together. The third terrain type shows smooth plains with few craters, indicating geological youth, where some process erased the impact record by covering or melting the older surface. These plains fill low areas and create transitions between the ancient cratered terrain and the grooved coronae, though their boundaries remain surprisingly sharp rather than gradual. The smoothness suggests material that flowed at some point in Miranda's history, either as liquid water or warm soft ice that could spread and fill topographic lows before freezing solid. The relative lack of craters indicates these plains formed more recently than the ancient terrain, though recently, in geological terms, still means hundreds of millions of years ago. Moving closer to the surface, approaching one particular region on Miranda's equator, the most dramatic feature on this strange moon comes into view. A cliff rises from the surface, its face nearly vertical, extending upward farther than seems possible for such a small world. The feature bears the name Verona Rupes, from Romeo and Juliet, like many Uranian features, and it represents the tallest known cliff in the entire solar system. The height measures 20 kilometers from base to top, nearly 12 miles of sheer ice and rock face dropping straight down. Standing at the edge of Verona Rupes and looking down creates a view unlike anything possible on Earth, as the cliff extends so far below that the bottom disappears into hazy distance, even in the thin, atmosphereless environment. The face shows striations and variations in color, suggesting different layers in Miranda's crust. The geology exposed in cross-section by whatever process created this enormous scarp. Small boulders and ice blocks rest near the edge, positioned where the slightest disturbance might send them tumbling over the side, into the abyss below. The horizon curves noticeably on this small world, the curvature far more pronounced than on larger moons, creating the sense of standing on a tiny sphere rather than on infinite ground. The low gravity changes everything about how this cliff functions and what would happen to anything falling from its edge. Miranda's surface gravity measures only about 1% of Earth's, so weak that a person could jump several meters high with minimal effort, and would fall very slowly after becoming airborne. Objects dropped from the top of Verona Rupes would accelerate downward, but far more slowly than on Earth, taking roughly 12 minutes to fall the full 20 kilometers before striking the bottom. The fall would feel almost gentle despite the distance, the acceleration so gradual that velocity builds slowly. Though by the time an object reaches the bottom, it would be traveling fast enough to shatter on impact. Jumping from the top of Verona Rupes, if one was somehow protected from vacuum and temperature, would create an experience entirely alien to anything possible on Earth. The cliff edge would drop away slowly as you separated from it, the descent beginning almost leisurely, the face of the cliff sliding past with increasing but still manageable speed. Minutes would pass, long enough to think about the situation, long enough to appreciate the geology of the cliff face as you descended, long enough for the fall to transform from initial fear to something approaching calm acceptance. The bottom would eventually rush up after those 12 minutes of falling, the impact inevitable, but preceded by such extended time that the experience would feel surreal rather than terrifying. The origin of Verona Rupes remains debated among planetary scientists, as creating such a tall cliff on such a small world requires unusual circumstances. One theory suggests the cliff formed when Miranda's interior expanded as it cooled and froze, the expansion cracking the surface and creating fault scarps where one section of crust rose relative to another section. Another theory proposes that the cliff represents the rim wall of an enormous ancient impact basin, with Verona Rupes marking the boundary of the depression created when a large object struck Miranda billions of years ago. A third possibility involves the breakup and reassembly scenario, where Miranda was shattered by a major impact and the pieces gradually came back together through mutual gravity, with Verona Rupes representing a boundary between two separate fragments that didn't quite fit together smoothly. The breakup and reassembly theory helps explain not just Verona Rupes, but the entire bizarre patchwork nature of Miranda's surface, though the theory remains controversial. If Miranda was disrupted by a major impact early in its history, the fragments would have continued orbiting Uranus roughly in the same location, eventually colliding gently with each other and sticking together through gravity. The reassembly would be chaotic, with pieces coming together in whatever orientation they happened to be in when they met, creating the jumbled terrain we observe. The different regions would represent different original pieces, each one retaining its own geological character, the boundaries between them marking where separate fragments joined. The coronae themselves might represent regions where tidal heating occurred during the reassembly period, when Miranda's orbit was more eccentric and Uranus's gravity flexed the moon's interior. The tidal forces would have been strongest in certain regions, depending on Miranda's shape and internal structure, creating localized melting or softening of ice that allowed it to flow and create the grooved patterns. The cratered terrain would represent pieces that remained cold and rigid throughout, never experiencing enough heating to erase their impact scars. The smooth plains could be later deposits of material that erupted or flowed from warmer regions and filled low areas after the main reassembly was complete. Walking across Miranda's surface near the boundary between different terrain types makes the strangeness visceral in a way that orbital observations cannot convey. The transition from heavily cratered dark terrain to bright grooved terrain occurs over distances of just a few hundred meters, far too abrupt for normal geological processes that usually create gradual transitions. The grooves themselves extend parallel to each other for kilometers, their regularity suggesting formation through consistent processes rather than random events. Yet the grooves end sharply at the boundary, with cratered terrain rather than fading gradually. Standing at such a boundary creates cognitive dissonance, as the eye expects the terrain types to blend, but instead observes an almost artificial-looking border. The temperature on Miranda's surface hovers around -213 degrees Celsius, cold enough that water ice becomes as hard as granite and maintains that hardness permanently, without seasonal variation. The lack of atmosphere means no wind disturbs the surface, no weather erodes the features, no precipitation falls to gradually bury geological structures. Everything on Miranda sits in perfect preservation, except for the slow accumulation of micrometeorite impacts and the even slower darkening from radiation bombardment. The landscape looks nearly identical today to how it appeared millions of years ago. The timescale of change so slow that human lifetimes become meaningless flickers in the moon's existence. The view from Miranda's surface toward Uranus reveals the planet hanging in the sky, though whether it appears overhead or near the horizon depends on which part of Miranda we stand on. Miranda orbits tidally locked to Uranus, like our moon to Earth. So one hemisphere always faces the planet, while the other hemisphere never sees it. From the Uranus-facing hemisphere, the planet dominates the sky as a pale blue-green disk, appearing about 4 times larger than our moon appears from Earth. The size difference reflecting Miranda's closer proximity to its planet, compared to our moon's distance from Earth. The planet's appearance changes slightly as Uranus rotates, though the rotation is slow enough that changes become noticeable only over hours. The orbit itself carries Miranda around Uranus at a distance of about 129,000 kilometers, completing one circuit every 1.4 Earth days. So, slightly longer than our own day. The orbital speed works out to about 6.7 kilometers per second, fast enough to circle Miranda's entire circumference in about 3.5 minutes if one could somehow travel at orbital velocity along the surface. The combination of orbital motion and tidal locking means that from Miranda's surface, Uranus appears to hang motionless in the sky, neither rising nor setting, maintaining the same position relative to the horizon throughout Miranda's day and year, which are the same length due to the tidal lock. The other moons occasionally pass across the sky as visible objects, with the 4 larger moons, Ariel, Umbriel, Titania, and Oberon, all orbiting farther out than Miranda, and therefore visible from Miranda's surface during parts of their orbits. These moons appear as bright points or small disks depending on their distance, their positions changing night by night as they proceed along their own orbital paths. The inner moons, those orbiting between Miranda and Uranus itself, would be difficult to see from Miranda's surface, because they stay close to the bright planet, and their small sizes make them faint even when they venture far enough from Uranus to be distinguishable. And so we have settled on Miranda, understanding its impossible cliffs and its patchwork surface, its 3 terrain types that refuse to blend smoothly, its possible history of disruption and reassembly that created the chaos we observe. The strangeness of this small moon establishes immediately that the Uranian system contains surprises, that these distant ice worlds refuse to conform to simple expectations, that each one will reveal distinct characteristics as we move outward through the family of satellites. Miranda serves as introduction to the system's diversity, a reminder that size does not determine interest, and that even the smallest moons can harbor profound mysteries that challenge our understanding of how worlds form and evolve over billions of years. Moving outward from Miranda through the Uranian moon system, the next major satellite orbits about 60,000 kilometers farther from the planet, completing one circuit every 2.5 Earth days, compared to Miranda's 1.4 days. This moon shows characteristics immediately distinguishable from Miranda's bizarre patchwork, presenting instead a surface that appears relatively uniform in overall character, while revealing its own particular geological history through features that speak of internal activity in the distant past. The name Ariel comes from Shakespeare's The Tempest and from Alexander Pope's The Rape of the Lock, connecting this ice world to literature, just as all Uranian moons take their names from the works of Shakespeare and Pope, rather than from classical mythology, like the moons of other planets. The first impression when approaching Ariel from space is of brightness, as this moon reflects more sunlight back into space than any other major Uranian satellite. The high reflectivity suggests relatively freshwater ice coating much of the surface, ice that has not yet been darkened by billions of years of radiation bombardment, and micrometeorite impacts that gradually darken exposed surfaces throughout the outer solar system. The brightness creates an initial paradox because Ariel orbits close enough to Uranus that it should experience intense radiation from particles trapped in the planet's magnetosphere. Radiation that normally darkens surface ice over time, yet somehow Ariel maintains its bright appearance despite this hostile environment. The resolution to the brightness paradox lies in Ariel's geological history, as the surface shows clear evidence of relatively recent resurfacing that covered older, darkened terrain with fresh ice. The resurfacing occurred through processes that operated hundreds of millions of years ago or more recently. Recent only in the geological sense, where events within the last billion years count as young compared to the solar system's 4.6 billion year age. The fresh ice explains the brightness, while raising new questions about what energy source powered the geological activity that brought fresh material to the surface. And examining the surface features in detail reveals the nature of those processes. Descending toward Ariel's surface reveals a landscape dominated by two major terrain types that, unlike Miranda's sharply bounded regions, transition more gradually into each other. The older terrain shows moderate cratering, with impact scars accumulated over billions of years, creating a surface marked by circular depressions of various sizes, from tiny bowl craters a few hundred meters across to larger structures tens of kilometers in diameter. The crater density falls well below what Miranda's ancient cratered terrain displays, indicating that Ariel's old terrain is actually younger than Miranda's oldest surfaces, with fewer impacts recorded because the surface formed or was renewed more recently. The craters that do exist show various states of preservation, some appearing fresh with sharp rims and clear ejector blankets, others appearing degraded and softened, as if some process partially erased them after formation. The younger terrain consists of smooth plains that fill low areas and create broad expanses with very few impact craters, indicating formation or resurfacing so recent that insufficient time has passed for many impacts to accumulate. The smooth plains appear brightest of all aerial surface types, suggesting the most recent emplacement of fresh ice, though recent still means hundreds of millions to perhaps a billion years in the past. The plains show subtle color variations in close-up images, with some areas appearing slightly bluish and others slightly more neutral gray. The color differences possibly indicating variations in ice composition or grain size that affect how sunlight scatters from the surface. The most dramatic features on aerial, the characteristics that distinguish this moon most clearly from its siblings, are the great canyon systems that cut across the surface in complex patterns. These canyons, technically called chasmata, using the Latin term for deep, steep-sided depressions, extend for hundreds of kilometers across aerial surface, creating valleys that drop several kilometers below the surrounding terrain. The canyon walls rise sharply from the valley floors, their faces showing layering and striations that reveal cross-sections of aerial's crust. The valley floors themselves appear smooth and relatively flat, covered with material that flowed into the canyons and settled there, creating surfaces distinct from the terrain through which the canyons cut. The largest canyon systems include features like Corrigan Chasma and Cupey Chasma, names drawn from folklore rather than Shakespeare, extending across aerial surface for 600 to 700 kilometers. The canyons reach depths of up to 10 kilometers in places, creating walls that tower over the valley floors like cliffs, though cliffs of ice rather than rock. Walking along the canyon floor and looking up at the walls rising kilometers on either side would create a sense of scale difficult to process. As the walls extend upward far beyond anything experienced in Earth canyons, and the ice composition gives them a different character than Earth's rocky gorges. The canyon formation on aerial most likely resulted from extensional tectonics, where the moon's surface stretched and cracked as its interior evolved and possibly expanded. When water freezes, it expands in volume compared to the liquid water it formed from. So if aerial's interior was originally warmer and contained liquid water that later froze, the expansion would stress the overlying crust and create fractures. The canyons formed where the crust pulled apart along parallel fracture zones, creating graben structures where blocks of crust dropped down between two parallel faults. The valley floors would represent the dropped blocks. The walls would be the fault scarps, and the smooth material on the floors could be deposits that flowed into the valleys after they formed. The smooth floor material raises interesting questions about what flowed and when, because liquid water is unstable on aerial's frozen surface, where temperatures never rise above -200 degrees Celsius. The most likely explanation involves cryovolcanism, where liquid water or water ammonia mixtures erupted from aerial's interior and flowed across the surface despite the freezing temperatures. The addition of ammonia to water lowers its freezing point substantially, creating a mixture that remains liquid at temperatures well below 0 Celsius, allowing it to flow like lava before eventually freezing solid. The smooth canyon floors would represent frozen cryovolcanic flows that erupted from vents along the canyon walls or floor. and spread across the valley bottom before solidifying. Evidence for cryovolcanism appears elsewhere on Ariel, beyond just the canyon floors, with sinuous features resembling lava channels visible in high-resolution images from the Voyager 2 flyby. These channels meander across the surface, following topographic lows, their paths suggesting flow of some fluid material that carved the channels as it moved. The channels connect to broader smooth patches that could represent flow deposits where the fluid ponded and froze after reaching flatter terrain. The overall pattern resembles volcanic landscapes on Earth, where lava flows from fissures and vents. But here, the flowing material was water, or water-ammonia mixture, rather than molten rock. The energy source that powered Ariel's cryovolcanism and created the heat necessary to melt ice in the interior remains somewhat mysterious, as Ariel's small size should have allowed its primordial heat to radiate away billions of years ago. The most likely heat source involves tidal heating, where Uranus's gravity flexes Ariel's interior as the moon orbits. If Ariel's orbit was more eccentric in the past, varying its distance from Uranus as it orbited, the changing tidal forces would have flexed the interior rhythmically, generating heat through friction, just as bending a wire repeatedly makes it warm. The heating could have maintained liquid water in Ariel's interior for extended periods, providing the source for cryovolcanic eruptions over hundreds of millions of years. The current orbit shows very low eccentricity, nearly circular, so if tidal heating occurred, it must have operated when the orbit was different, and then the orbit circularized over time through tidal evolution. Gravitational interactions with other Uranian moons could have maintained orbital eccentricity for extended periods if Ariel was locked in orbital resonances with its siblings, where orbital periods maintained simple numerical ratios that created recurring gravitational tugs. The resonances would have prevented the orbit from circularizing and maintained the eccentricity necessary for tidal heating until something broke the resonance and allowed the orbit to become circular. The surface also shows fascinating structural features called fault scarps, where the ground on one side of a linear feature stands higher than the ground on the other side, creating step-like cliffs that extend for tens or hundreds of kilometers. These faults indicate vertical motion of crustal blocks along fracture zones, with some blocks rising relative to others, or some blocks dropping to create the elevation differences. The faults often parallel the major canyons, suggesting they formed through the same extensional processes that created the canyon systems, perhaps representing early stages of rifting that didn't fully develop into deep valleys. Walking across Ariel's surface near one of these fault scarps allows direct observation of the moon's crustal structure exposed in the cliff face. The ice shows varying textures and possibly different colors at different depths, suggesting either compositional variations or different grain sizes created during different episodes of freezing or recrystallization. Small impact craters dot the surface at all scales, with the smallest visible craters only meters across, representing the most recent impacts, while larger craters record events from millions or billions of years ago. The variety in crater preservation states tells a story of gradual surface evolution, with some craters remaining sharp and well-defined, while others appear softened and degraded by processes that modify Ariel's surface over geological time. The view toward Uranus from Ariel's surface shows the planet appearing smaller than from Miranda's closer orbit, but still prominent, subtending about 2.5 degrees of arc compared to our moon's half degree when viewed from Earth. The planet's pale blue-green color comes from methane in its atmosphere, absorbing red light and reflecting blue and green wavelengths back to space, creating the distinctive coloration that makes Uranus recognizable, even in images where its disk appears without obvious features. The planet shows subtle banding in enhanced images, atmospheric zones and belts created by wind patterns in its hydrogen-helium atmosphere, though the banding remains much more subtle than the vivid belts and zones of Jupiter. The distance from Ariel to Uranus measures approximately 191,000 kilometers, placing Ariel farther out than Miranda, but closer than the three larger moons, Umbriel, Titania, and Oberon. The orbital period of 2.5 days means that from Ariel's tidally locked surface, Uranus completes slightly more than 2 full rotations during each of Ariel's orbits, creating a slow progression of features across the planet's disk as Ariel circles and Uranus rotates. The Uranus-facing hemisphere of Ariel enjoys a constant view of the planet, while the far hemisphere never sees Uranus at all, the tidal lock creating permanent division between the near and far sides, just as on our own moon. The possibility that Ariel once harbored a subsurface ocean adds speculative interest to this moon's history, as the evidence for cryovolcanism and geological activity suggests. Liquid water existed at depth for at least some portion of the moon's history. An ocean beneath an ice shell would create conditions similar to those on Jupiter's moon Europa or Saturn's moon Enceladus, where liquid water contacts rocky material at the ocean floor, potentially enabling interesting chemistry. Whether such an ocean could have persisted long enough for any complex chemistry to develop remains unknown, and whether any remnant liquid water survives today in Ariel's interior cannot be determined from available data. The current state shows a frozen world where geological activity has long since ceased. The bright surface ice, slowly darkening under radiation bombardment, the canyons sitting empty and cold, the cryovolcanic vents sealed shut by freezing temperatures that never rise high enough to permit liquid water. Ariel continues its orbit as it has for billions of years, the surface changing only through the slow accumulation of impact craters and the gradual radiation darkening that will eventually mute the brightness that currently distinguishes this moon. The mysteries remain encoded in the frozen geology, waiting for future missions to visit and study in detail what the brief Voyager encounter could only glimpse. And so we leave Ariel behind, carrying understanding of its bright ice and deep canyons, its smooth plains and ancient faults, its evidence of past activity contrasting with current frozen stillness. The next moon outward presents a dramatic contrast in almost every measurable way, as if nature deliberately created an opposite to Ariel's brightness and youth while maintaining similar size and orbital distance. And we move toward that darker world to understand what makes it so different. The third major moon encountered when moving outward from Uranus presents immediately as Ariel's opposite, a world where darkness rather than brightness characterizes the surface, and where ancient terrain dominates rather than fresh ice. The approach from space reveals a grey sphere reflecting only about 16% of the sunlight that strikes it, making Umbriel the darkest of all Uranus's major moons and one of the darkest large satellites in the entire solar system. The low reflectivity creates mystery before any surface details become visible, raising questions about what material coats this world and what processes created such a dark surface on a moon presumably made of water ice, like its siblings. Closer approach reveals that Umbriel's darkness comes not from shadows or from lack of illumination, but from the intrinsic low reflectivity of the surface material itself, which appears uniformly charcoal grey across nearly the entire visible hemisphere. The surface shows heavy cratering with impact scars accumulated over billions of years, creating a landscape marked by circular depressions of every size, from the resolution limit of our imaging up to structures hundreds of kilometers across. The crater density approaches saturation in many regions, meaning new impacts cannot create fresh craters without obliterating older ones, indicating this surface has remained largely unchanged for perhaps 3 to 4 billion years. The uniformity surprises as much as the darkness, because, unlike Miranda's patchwork or Ariel's bright and dark terrain types, Umbriel presents an almost monotonous consistency across its entire visible face. No major canyon systems cut across the surface. No bright rays extend from fresh impact craters. No obvious signs of cryovolcanism or tectonic activity break the ancient heavily cratered terrain. The consistency extends across different crater sizes and different regions, creating the impression of a world that froze geologically very early in its history and has changed only through the accumulation of impact craters since that early freeze. One feature breaks the monotony and adds mystery to Umbriel's dark face. A bright ring near the top of the visible hemisphere in Voyager 2 images, standing out against the dark surroundings like a beacon. The feature sits near the center of a crater called Wunda, a depression about 130 kilometers in diameter, showing no other unusual characteristics except for the bright material at its center. The bright ring appears to be a deposit of material, different from the dark surface that covers the rest of Umbriel. Though what the material is and how it got there remain unclear from the limited images available. The bright ring in Wunda crater has generated various theories about its origin and composition, though without additional data confirming or eliminating possibilities. All explanations remain speculative. One theory suggests the brightness comes from relatively fresh water ice, exposed by an impact that punched through a dark surface layer to reveal cleaner ice beneath. Another possibility involves frost deposition, where volatile materials condensed preferentially in Wunda's location due to some local condition that made frost formation favorable there, but not elsewhere on Umbriel's surface. A third speculation proposes that the bright material erupted from Umbriel's interior through cryovolcanism, localized in this one crater, bringing fresh material to the surface in this isolated location, while the rest of Umbriel remained geologically dead. The darkness of Umbriel's surface likely results from carbon-rich material or organic compounds produced by radiation processing of methane and other simple molecules in the ice. When high-energy particles or ultraviolet light strikes methane frozen in surface ice, the radiation can break apart the methane molecules and create more complex carbon compounds that appear dark brown or black. Over billions of years of radiation exposure, these dark compounds accumulate on the surface, creating a coating that reduces reflectivity and gives the surface its characteristic charcoal grey appearance. The process operates on all the Uranian moons to some degree, but Umbriel appears particularly dark either because it has accumulated more dark material or because it lacks processes that resurface and refresh the ice. The absence of bright crater rays on Umbriel contrasts sharply with our own moon, where fresh impact craters are surrounded by bright streaks of ejecta material extending radially outward from the impact site. On the Moon, these rays represent fresh material excavated from beneath the darkened surface layer and splashed across the surrounding terrain, creating brightness contrasts that fade over millions of years as radiation and micrometeorite impacts gradually darken the ray material. Umbriel's lack of prominent rays suggests either that impacts do not excavate bright material from beneath the dark surface, or that any bright ejecta darkens so quickly that rays never become prominent before fading. The possibility that Umbriel's dark layer extends deep into the crust, rather than representing just a thin surface coating, could explain the lack of bright rays. Because if the dark material pervades the upper kilometers of ice, then impacts would excavate dark material and create dark rays that blend invisibly with the dark surroundings. This scenario suggests Umbriel's dark compounds are not merely a surface coating, but rather permeate the ice throughout the outer layers of the Moon, either mixed in during formation or created through radiation processing that affected deep ice by penetrating radiation over billions of years. The size of Umbriel, at 1,169 kilometers diameter, makes it nearly identical to Ariel at 1,158 kilometers. Yet, the two moons appear entirely different in both brightness and geological character. This similarity in size, the difference in appearance, creates one of Umbriel's major mysteries. Why did two similarly sized moons at similar distances from Uranus evolve so differently? Ariel shows evidence of past geological activity, with its canyons and smooth plains, while Umbriel appears geologically dead, with no obvious signs of resurfacing or tectonic activity. Ariel maintains a relatively bright surface, suggesting recent ice exposure, while Umbriel's dark surface suggests ancient, unchanging terrain. The mystery deepens when we consider that both moons likely formed from similar materials and experienced similar radiation environments. Yet they arrived at opposite endpoints in terms of geological evolution and surface appearance. One possibility involves differences in internal heat, where Ariel retained or generated more heat than Umbriel through tidal heating or radioactive decay, maintaining geological activity that resurfaced Ariel's ice, while Umbriel cooled quickly and froze geologically. Another possibility suggests that Umbriel experienced some event or process that created its thick, dark layer, perhaps a period of intense bombardment by dark material, or a process that selectively darkened Umbriel's surface while leaving Ariel's ice relatively pristine. Walking across Umbriel's dark surface creates an experience of profound antiquity, as every vista shows heavily cratered terrain that has remained essentially unchanged for billions of years. The crater walls rise around impact depressions, their slopes gentle from billions of years of micrometeorite bombardment that gradually softens sharp features. creating landscapes where even relatively fresh craters appear somewhat degraded. The dark material absorbs most incoming light, making the surface appear to swallow illumination rather than reflecting it brightly, creating a landscape that feels heavier and more oppressive than the bright ice of Ariel, despite both being the same temperature and having the same composition beneath any surface coatings. The view toward Uranus from Umbriel's surface shows the planet appearing slightly smaller than from Ariel due to Umbriel's greater orbital distance of 266,000 kilometers, about 75,000 kilometers further from the planet than Ariel orbits. The orbital period extends to 4.1 days, nearly twice Ariel's period, reflecting the greater distance and the weaker gravitational influence at that range. Like all major Uranian moons, Umbriel is tidally locked with one hemisphere permanently facing Uranus and the other permanently facing away. The synchronous rotation established billions of years ago through tidal forces that gradually slowed whatever initial rotation Umbriel possessed, until the rotation period matched the orbital period. The Uranian system's sideways configuration means that, as Umbriel orbits, it experiences the planet's extreme seasons, where each pole receives continuous sunlight for 42 years, followed by 42 years of darkness. During the periods when sunlight strikes Umbriel's south or north pole directly, that pole remains in continuous illumination for Earth decades, while the opposite pole stays in continuous darkness, creating seasonal temperature variations that differ dramatically from the day-night cycles familiar on Earth. These seasonal cycles affect surface temperatures and might cause volatile materials to migrate from the illuminated pole toward the dark pole. Though on Umbriel's ancient cold surface, such migration would be minimal, the lack of atmosphere on Umbriel, like all the major Uranian moons, means that nothing mediates temperature or distributes heat, and no weather occurs beyond the slow rain of micrometeorites that strikes continuously at random locations. The silence is absolute, as no air exists to carry sound, and the stillness is perfect, as no wind disturbs the surface or moves surface material. Time passes in geological rhythms where changes occur over millions of years through the accumulation of impacts and the slow radiation darkening of any materials that somehow escape the general darkness, characterizing the moon's appearance. The ancient surface also means that any features present on Umbriel are very old, representing geological events that occurred billions of years ago rather than recently. The large craters record impacts from when the solar system was young and debris was still common, when objects left over from planetary formation collided frequently with the newly formed moons. The survival of these ancient features without significant modification indicates that Umbriel lacks the geological activity that would erase or modify them. The tectonic processes that would create faults and valleys, the cryovolcanism that would bury old terrain under fresh flows. Umbriel sits frozen in time, a museum of ancient solar system history, written in craters. And so we leave this dark, mysterious moon behind, carrying questions about why it appears so different from Ariel, despite their similarities in size and location. Understanding that sometimes nature creates twins that evolve divergently and arrive at opposite characteristics despite shared beginnings. The journey outward continues toward the two largest moons in the Uranian system, giants that dwarf Umbriel and Ariel and Miranda, worlds large enough enough to show their own distinctive characters and histories. The two largest moons of Uranus orbit beyond Umbriel, in the outer reaches of the major satellite system, both similar in size to each other, yet each displaying distinct geological character and history. Titania, slightly larger of the pair, holds the title of Uranus's largest moon, though it remains far smaller than the truly giant satellites of Jupiter and Saturn. Oberon follows closely in size, the second largest Uranian moon, orbiting even farther out and completing the roster of the 5 major moons discovered before modern spacecraft and advanced telescopes revealed the system's smaller members. Approaching Titania from space reveals a world substantially larger than the inner moons, with a diameter of 1,578 kilometers, making it roughly half the size of our own moon and larger than all of Uranus's other satellites. The surface shows moderate cratering, with impact scars visible at all scales, but at lower density than Umbriel's saturated ancient terrain, indicating that geological processes operated more recently on Titania and renewed at least portions of the surface after the heavy bombardment period ended. The overall appearance suggests a world that experienced geological evolution extending later into its history than Umbriel's early freeze, creating a surface that records both ancient impacts and more recent modification. The most dramatic features visible from orbit are the great fault valleys cutting across Titania's surface, massive canyon systems that dwarf even Ariel's impressive chasms in scale and extent. The Messina Chasmata extends for roughly 1,500 kilometers across Titania's surface, a canyon system comparable in length to the entire diameter of the moon, creating a scar that wraps nearly a quarter of the way around the world. The valleys reach depths of several kilometers in places, with steep walls rising from flat floors, much like Ariel's canyons, suggesting similar formation through extensional tectonics, where Titania's surface pulled apart as the interior evolved. The formation of such enormous canyons on Titania likely involved the same basic process that created Ariel's valleys: expansion of the interior as liquid water froze and increased in volume, stressing the overlying crust until it fractured. The scale of Titania's canyons suggests even more extensive internal evolution than Ariel experienced, possibly indicating a larger initial liquid water ocean that froze over longer timescales, creating sustained expansion that opened the great rifts we observe. The canyon floors show smooth deposits similar to those on Ariel, suggesting cryovolcanic flows filled the valleys after they formed, bringing liquid or slushy material from depth that froze into the flat plains now visible. The surface also shows regions of smooth plains outside the major canyons, areas where fresh ice apparently covered older terrain through processes that could include cryovolcanic flows spreading across low regions or possibly snow-like deposition of frost that accumulated and compacted over time. These smooth plains show fewer craters than heavily cratered regions nearby, confirming their younger age and indicating that Titania's geological activity continued long enough to create these deposits after the period of heavy bombardment ended. The contrast between heavily cratered ancient terrain and lightly cratered smooth plains creates visual interest and tells a story of episodic activity where geological processes operated intermittently rather than continuously. The brightness of Titania's surface exceeds Umbriel's dark grey, but falls short of Ariel's high reflectivity, placing Titania in the middle of the range displayed by Uranus's major moons. The moderate brightness suggests a surface that has undergone some darkening through radiation processing, but retains enough fresh ice exposure to maintain reasonable reflectivity. The balance between ancient cratered terrain and younger smooth plains creates a mixed surface where different regions show different brightnesses depending on their ages and exposure histories. Moving outward from Titania to Oberon requires crossing another 148,000 kilometers of space, and the outermost of the 5 major moons reveals itself as distinctly different from Titania, despite their similar sizes. Oberon's diameter of 1,523 kilometers makes it only slightly smaller than Titania, the 2 moons forming a giant pair at the outer edge of the major satellite system. The surface appearance differs markedly from Titania's, showing heavier cratering with less evidence of geological activity that would have erased or modified ancient terrain. The most heavily cratered regions on Oberon show impact densities approaching Umbriel's levels, indicating very old surfaces that have accumulated scars over billions of years without significant resurfacing. The craters display various states of preservation, with some showing sharp, well-defined rims and clear ejector blankets, while others appear degraded and softened by time and subsequent impacts. The size range extends from small bowl craters at the limit of visibility up to enormous structures hundreds of kilometers across, including one crater nearly 300 kilometers in diameter that dominates the visible hemisphere in Voyager images. One particularly interesting feature on Oberon is a mountain or massif that appears in images as a bright peak rising from the surface, visible near the terminator, where shadows reveal topographic relief. The mountain reaches approximately 6 kilometers above the surrounding terrain, making it one of the tallest peaks known on any Uranian moon, and comparable in height to some of Earth's major mountains, though in a much lower gravity environment. The origin of this mountain remains uncertain, with possibilities including the central peak of a large ancient impact crater, an uplift from tectonic processes, or possibly a remnant of some early geological process that created high terrain, later preserved, while surrounding areas were lowered through impact erosion. Oberon's surface shows dark patches within some crater floors, a feature that intrigues scientists because it suggests material from the interior reached the surface through impact excavation, or possibly through cryovolcanic activity localized within craters. The dark material appears darker than the surrounding terrain and concentrated in specific locations rather than distributed uniformly, suggesting it represents a different composition, or perhaps contamination from impactors rather than native Oberonian material. Understanding what this dark material is and where it came from requires more detailed observations than the brief Voyager encounter provided. The overall impression of Oberon is of a world that froze geologically very early and has remained largely inactive since, recording billions of years of impact history without the resurfacing that modified Titania and Ariel. The heavy cratering and lack of obvious tectonic features suggests Oberon cooled quickly after formation and never experienced the prolonged tidal heating or internal evolution that kept other moons active longer. The ancient surface makes Oberon a valuable record of conditions in the early solar system, as the craters preserve information about the bombardment history that all the Uranian moons experienced, but that most other moons have partially erased through geological activity. The view toward Uranus from Oberon's surface shows the planet appearing smaller than from any of the inner major moons due to Oberon's great orbital distance of 584,000 kilometers, more than 4 times farther than Miranda orbits. The planet still appears substantially larger than our moon appears from Earth, subtending about 1 degree of arc and showing its pale blue-green color clearly. But the sense of looming proximity that characterizes views from the inner moons gives way to more distant perspective. The orbital period extends to 13.5 days, reflecting both the greater distance and the weaker gravitational force at that range, making Oberon's year more than 9 times longer than Miranda's, despite both orbiting the same planet. The composition of both Titania and Oberon appears similar to the inner major moons, with roughly equal mixtures of water, ice, and rocky material, creating bulk densities around 1.7 grams per cubic centimeter, substantially lower than pure rock, but higher than pure water ice. This composition suggests these moons formed from the same population of materials as Miranda, Ariel, and Umbriel, despite their larger sizes and different geological histories. The similarity in composition but difference in geological evolution demonstrates that size alone does not determine a moon's history, as other factors including orbital position, tidal heating, and possibly random events like major impacts also influenced how each moon evolved. The possibility that both Titania and Oberon once harbored subsurface oceans beneath their ice crusts remains plausible based on their sizes, as larger moons retain internal heat longer and have better chances of maintaining liquid water at depth. The evidence for cryovolcanism and extension on Titania suggests liquid water existed there, at least during some portion of its history, while Oberon's more ancient appearance might indicate either that it never had an ocean or that any ocean froze earlier in the moon's history. Whether any liquid water persists today, deep within either moon, cannot be determined from available data, though the current frozen surfaces and lack of active geology suggest that any remnant liquid regions are small and isolated, if they exist at all. Walking across the surfaces of these giant moons creates different experiences despite their proximity in size. As Titania's canyons and smooth plains offer varied terrain, while Oberon's heavily cratered landscapes emphasize antiquity and preservation. Both worlds share the extreme cold that characterizes all Uranian moons, with surface temperatures hovering around -200 degrees Celsius, where water, ice, achieves granite-like hardness and maintains that strength permanently. Both are tidally locked to Uranus, keeping one hemisphere permanently facing the planet, while the other faces eternally away, creating populations who, if any existed, would either always see Uranus overhead or never see it at all, depending on which hemisphere they inhabited. And so we leave the giant pair behind, having explored all 5 major moons that dominate the Uranian satellite system by mass and size, each one a distinct world with its own character and history. Beyond these giants orbit populations of smaller moons, some close to Uranus and some very distant. And we turn our attention now to these lesser satellites to understand the full diversity of worlds that accompany the sideways planet through its orbit around the Sun. Between Uranus itself and Miranda's orbit lies a crowded zone where 13 small moons circle the planet at distances ranging from about 50,000 to 86,000 kilometers, completing orbits measured in hours rather than days due to their proximity to the planet's strong gravitational field. These inner moons remained unknown until the Voyager 2 encounter in 1986, when careful scrutiny of images revealed small dark objects orbiting among the planet's ring system and just beyond the ring's outer edge. The discovery of these moons expanded the Uranian satellite system substantially and revealed a population of small worlds whose existence had been completely unsuspected before the spacecraft arrived. The names of these inner moons continue the Shakespearean tradition established for the major satellites, but draw from a wider range of plays and poems: Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Cupid, Belinda, Perdita, Puck, and Mab. The names evoke characters from tragedies and comedies, connecting these small ice worlds to literature in a tradition unique among planetary satellites. As every other planet's moons draw names from classical mythology, while Uranus's moons alone inhabit Shakespeare's universe. The literary connection adds a layer of meaning to these otherwise unremarkable small bodies, transforming designation of objects into something that resonates with human culture. The largest of the inner moons is Puck, named for the mischievous sprite from A Midsummer Night's Dream. Measuring about 162 kilometers across and representing the only inner moon large enough for gravity to have pulled it into a roughly spherical shape. The smaller inner moons show irregular shapes, resembling potatoes or other oblong forms rather than spheres, their self-gravity too weak to overcome the mechanical strength of ice and pull them into round configurations. Puck itself shows a lumpy potato shape in Voyager images, despite being the largest of the group, suggesting either that it formed through collision and accretion of fragments rather than gradual accumulation, or that its composition includes enough rocky material to increase strength and prevent complete rounding. The surface of Puck, the only inner moon imaged in sufficient detail to show features, appears dark grey and heavily cratered, resembling a miniature version of Umbriel's ancient terrain. The dark colour suggests similar radiation processing has created carbon-rich compounds on Puck's surface, or possibly that the moon formed from darker material than the major satellites further out. The heavy cratering indicates Puck's surface is very old, having accumulated impact scars over billions of years without geological activity to erase or modify them. The craters range from the resolution limit of the images down to sizes comparable to Puck's radius, including several large depressions that must have come close to shattering the small moon. The other inner moons, smaller than Puck and more distant from Uranus, show little detail in available images beyond rough size estimates and basic shapes. Their sizes range from about 18 kilometers for the smallest known members up to around 130 kilometers for the larger ones, placing them all in the category of minor satellites rather than major moons. The orbits of these small bodies are tightly packed in the relatively narrow zone between the rings and Miranda, creating a crowded, dynamical environment where gravitational perturbations from neighbors can affect orbital stability over long timescales. Two of the inner moons, Cordelia and Ophelia, serve an important function in the Uranian system as shepherd moons for the Epsilon ring, the brightest and densest of Uranus's narrow rings. Cordelia orbits just inside the Epsilon ring, while Ophelia orbits just outside it. And the gravitational influence of both moons helps confine the ring particles to a narrow band and prevents them from spreading outward or inward over time. The shepherd mechanism works through resonances where ring particles at the inner edge of the ring experience periodic gravitational tugs from Ophelia that push them inward, while particles at the outer edge experience tugs from Cordelia that push them outward, the combined effect maintaining the ring's narrow width. The discovery of shepherd moons at Uranus confirmed theories developed to explain Saturn's narrow F-ring, where the moons Prometheus and Pandora serve similar shepherding roles. The mechanism demonstrates how small moons can have significant dynamical effects despite their tiny masses, controlling the distribution and stability of nearby ring material through resonant gravitational interactions. The shepherd moons themselves likely formed from ring material that accreted into larger bodies. Or possibly, they represent captured material that became trapped in orbits that happened to lie near ring edges and then began shepherding the rings they found themselves near. The orbits of the inner moons show some interesting characteristics that reveal the complex gravitational environment close to Uranus. The orbital periods range from about 8 hours for Cordelia, the innermost moon, up to about 18 hours for Mab, the outermost known inner moon, with the periods determined by the balance between orbital speed and gravitational force at each distance. The moons all orbit in the same direction as Uranus rotates, and in the planet's equatorial plane, indicating they formed from material orbiting the planet, rather than being captured from elsewhere. This orderly configuration contrasts with the chaotic arrangement of the irregular outer moons we will explore later. The close proximity to Uranus means these inner moons orbit within the planet's Roche limit for rocky material, a boundary inside which tidal forces can tear apart bodies held together only by gravity rather than material strength. The survival of these moons inside the Roche limit indicates they possess sufficient internal strength to resist tidal disruption, suggesting they are coherent bodies rather than loose rubble piles. This strength likely comes from ice binding the moons together. As water, ice at the low temperatures characteristic of the Uranian system develops substantial mechanical strength that allows it to support stress without fracturing. The future of the inner moon system includes the possibility of collisions, as the crowded orbital zone and gravitational perturbations between neighbors create an unstable configuration over very long timescales. Computer simulations of the inner moon orbits suggest that some moons will eventually collide with each other or with the rings, perhaps within the next few million to 100 million years, depending on the specific assumptions used in the modeling. When collisions occur, the low-impact velocities resulting from the moon's nearby orbits mean the collisions will be relatively gentle, likely producing fragments that reaccrete through mutual gravity to form new moons rather than ejecting material completely from the system. This collisional evolution may have already occurred multiple times in the inner moon system's history, with the current population representing the latest generation of bodies that formed from fragments of earlier moons. The process creates a constantly renewing population, where individual moons have finite lifetimes, measured in tens or hundreds of millions of years, before collisions disrupt them. But the system as a whole persists, with new moons forming from the debris of destroyed ones. The concept of renewable satellite populations, where moons are destroyed and reformed cyclically, represents a relatively new idea in planetary science, emerging from studies of crowded moon systems, like Uranus's inner satellites and Saturn's similar small moon populations. The viewing of inner moons from the surface of Miranda or the other major satellites would show them as bright points moving relatively rapidly across the sky, distinguishable from stars by their motion and their positions, always remaining close to the planet. From Uranus itself, if anyone stood on the solid core far below the cloud tops, the inner moons would zip past overhead in a matter of hours, rising in the east and setting in the west, due to their orbital motion surpassing the planet's 17-hour rotation period. The moons would appear as small disks or points depending on their size and distance. At any moment, their steady motion creating a sense of dynamic activity, contrasting with the more stately progression of the major moons. The composition of the inner moons likely resembles the composition of the ring material, as both probably originated from similar parent bodies that fragmented through impacts or tidal disruption. The rings and inner moons together represent a reservoir of material trapped close to Uranus, perhaps material left over from the planet's formation, or perhaps debris from a destroyed moon or captured object that broke apart near the planet. The dark color of Puck, and presumably the other inner moons, suggests they contain substantial amounts of dark material, possibly carbonaceous compounds, or perhaps material from a different source region in the solar system that became incorporated into the Uranian system. And so we leave the crowded inner zone and its 13 small moons, understanding them as a dynamic population orbiting close to their planet, shepherding rings and occasionally colliding, forming and reforming through billions of years of evolution. The journey outward from the major moons now carries us far beyond Titania and Oberon, out to the realm of the irregular satellites, a completely different population of small moons with different origins and different characteristics. Far beyond the orbits of the 5 major moons and the 13 inner satellites, a third population of Uranian moons wanders on distant paths that take them millions of kilometers from the planet and years to complete single orbits. These 10 outer moons differ fundamentally from the regular satellites we have explored, showing characteristics that immediately identify them as outsiders rather than native Uranians, captured visitors that originated elsewhere in the solar system and became gravitationally bound to Uranus through 3-body interactions during the chaotic, early history of planetary formation. The irregular moons, as this population is called, orbit in the opposite direction from the planet's rotation and from the regular satellites, creating the clearest signature of their captured status. The retrograde orbits, where moons circle the planet in the direction opposite to the planet's rotation, cannot result from formation within a disk of material orbiting Uranus, because material in such a disk would naturally orbit in the same direction as the planet rotates. The retrograde motion indicates these moons approached Uranus from outside its gravitational sphere and became captured through interactions involving the planet, the Sun, and the approaching object. The capture process requires energy dissipation to slow the object enough that it cannot escape Uranus's gravity after passing close to the planet, with mechanisms including gas drag if the capture occurred early, when Uranus still possessed an extended atmosphere, or three-body interactions where the object's trajectory brought it close to the planet at exactly the right moment that gravitational interactions with the Sun helped capture it. The largest irregular moon is Sycorax, named for Caliban's mother in Shakespeare's The Tempest, measuring about 150 kilometers in diameter, based on estimates from brightness and assumed reflectivity. The distance from Uranus varies considerably due to the moon's highly eccentric orbit, ranging from about 6 million kilometers at closest approach to about 14 million kilometers at the farthest point, creating an enormous variation in the moon's distance from the planet throughout each orbit. The orbital period extends to about 1,288 days, roughly 3.5 Earth years, meaning anyone living on Sycorax would measure years in Earth years and would see Uranus appear as a distant pale blue star rather than a nearby planetary disk. The other irregular moons bear similarly exotic Shakespearean names: Caliban, Prospero, Setebos, Stefano, Trinculo, Francisco, Ferdinand, Margaret. And Perdita, wait, that's wrong. Perdita is an inner moon, so the list should be Francisco, Ferdinand, Margaret. The names come from characters in The Tempest primarily, with a few from other plays, continuing the literary theme while drawing from the darker, more mysterious parts of Shakespeare's works appropriate for these distant wandering moons. The sizes range from about 150 kilometers for Sycorax, down to perhaps 12 to 18 kilometers for the smallest discovered members, with the size estimates uncertain because the moons are too distant and faint for direct measurement and must be inferred from brightness, assuming plausible reflectivity values. The colors of the irregular moons differ noticeably from the neutral grey tones characteristic of the regular satellites, with several irregular moons showing distinctly reddish or light red colors in filtered images. The reddish coloration suggests surface materials different from the water ice and rocky mixture dominating the regular satellites, possibly indicating organic-rich compositions similar to materials found in comets and in the Kuiper belt beyond Neptune's orbit. The color difference supports the captured object hypothesis for the irregular moon's origins, as objects captured from the outer solar system would be expected to show compositions different from moons that formed in orbit around Uranus. The orbital characteristics of the irregular moons show high inclinations relative to Uranus's equatorial plane, with some moons orbiting at angles exceeding 100 degrees from the equator, meaning their orbits tilt dramatically out of the neat alignment shown by the regular satellites. The high inclinations, combined with the retrograde motion and the eccentric elliptical orbits, all point toward capture origins, as these orbital elements preserve information about the conditions under which the captures occurred. Objects captured while approaching from random directions would naturally show a range of inclinations and orbital orientations, depending on the details of each capture event. The environment on the surface of an irregular moon like Sycorax differs profoundly from conditions on the inner regular satellites. Starting with the view of Uranus, from Sycorax's distant vantage point, Uranus appears as a bright, pale blue point of light, showing a distinct disk through any optical aid, but appearing star-like to the unaided eye. The planet would show phases like Venus shows phases when viewed from Earth, because Sycorax's distance and orbital motion mean it sometimes sees Uranus illuminated from behind, and sometimes sees it backlit by the distant sun. The phase changes occur slowly over the multi-year orbital period, creating a stately progression from full Uranus when Sycorax is opposite the sun, from the planet through crescent phases when Sycorax lies between the planet and the sun. The sun itself appears much dimmer from the Uranian system than from Earth, providing only about 1/400th the illumination we receive on our home world. And from Sycorax's distant orbit, the sun appears as merely the brightest star in the sky, rather than a dominant light source. The illumination reaching Sycorax's surface measures comparable to bright twilight on Earth, sufficient for human eyes to see clearly after adapting, but far dimmer than normal daylight. The weak sunlight combined with Sycorax's slow rotation, likely matching its orbital period through tidal locking to Uranus, creates surface conditions where temperatures vary between the illuminated and dark hemispheres, but overall remain uniformly frigid at values around -220 degrees Celsius or colder. The surface composition of the irregular moons remains uncertain due to the limited observational data available, with only rough color estimates and brightness measurements informing our understanding. The reddish colors suggest organic compounds called tholins, complex molecules formed through radiation processing of simpler compounds like methane and nitrogen, creating the same types of materials that color the surfaces of Kuiper Belt objects and Pluto's moon Charon. If this interpretation is correct, then the irregular moons represent samples of outer solar system material captured and preserved in orbit around Uranus, offering glimpses of the chemical composition characteristic of the region beyond Neptune. The question of where the irregular moons originated before their capture leads to theories about Kuiper Belt objects or scattered disk objects that approached close to Uranus during the early solar system, when planetary orbits were less stable and objects migrated inward and outward through gravitational interactions. The NICE model of solar system evolution suggests that the giant planets migrated substantially from their formation locations, with Jupiter moving inward slightly, while Saturn, Uranus, and Neptune moved outward considerably, stirring up the population of small bodies in the outer solar system and scattering them throughout the planetary region. During this chaotic period, close encounters between planets and scattered objects would have been common, creating opportunities for captures when objects happen to pass near planets at favorable velocities and geometries. The survival of the irregular moons over billions of years since their capture indicates orbital stability, despite the complex gravitational environment, including perturbations from the Sun and from the regular satellite system. The high eccentricities and inclinations create situations where the irregular moon orbits precess slowly around Uranus, the orbital planes rotating and the periapsis points shifting over thousands of years. But these precessions maintain the moons in bound orbits rather than allowing them to escape or collide with the planet. The long-term stability allows these captured visitors to remain as permanent members of the Uranian system, having arrived billions of years ago and remaining indefinitely into the future, barring unlikely disruptions from passing stars or major changes in the solar system's configuration. The irregular moons provide scientific value beyond their intrinsic interest as captured Kuiper belt objects, serving as test cases for understanding satellite capture mechanisms and orbital evolution in general. The study of how captures occur and how captured satellites' orbits evolve over time informs our understanding of similar populations around the other giant planets, all of which host their own irregular satellite systems with similar characteristics. Jupiter alone has over 80 irregular moons, while Saturn and Neptune also host substantial populations. And the common characteristics across all these systems suggest similar capture processes operated throughout the outer solar system during the early period when planetary orbits were still evolving. And so we leave the distant, irregular moons on their lonely retrograde orbits, wandering for years around Uranus, on paths that take them millions of kilometers from the planet before returning to closer approaches, forever circling but never truly belonging to the neat, ordered system of regular satellites closer in. Their presence adds diversity to the Uranian system and provides connections to the wider outer solar system. But understanding how all these satellites, regular and irregular alike, came to exist requires looking back billions of years to the system's formation. The story of how Uranus's 28 moons came to exist begins 4.6 billion years ago, when the solar system was young and the planets were still forming from the disk of gas and dust that orbited the newly ignited sun. Uranus formed in the outer solar system beyond the frost line, the distance from the sun where temperatures dropped low enough for water and other volatiles to condense into ice, allowing the planet to accumulate both rocky material and volatile ices as it grew. The planet's formation likely occurred through a two-stage process, where a solid core of rock and ice formed first, growing through accretion of countless smaller bodies, and then the core's gravity captured gas from the surrounding nebula to create the hydrogen and helium atmosphere that now dominates the planet's mass. During and after Uranus's formation, a disk of material orbited the young planet, much as the solar nebula orbited the sun, creating a miniature planetary system where moons could form through the same basic processes that created the planets themselves. The regular satellites, those moons showing orderly circular orbits aligned with Uranus's equator, formed from this circumplanetary disk through gradual accretion where small particles stuck together and grew through countless collisions. The disk material likely consisted of rock and ice in proportions similar to what we observe in the moons today, the composition reflecting both the local conditions around Uranus and the composition of material in this region of the solar system. The 5 major moons, Miranda through Oberon, grew to their current sizes through this accretion process, each one sweeping up material from its particular orbital distance and incorporating that material into growing bodies. The moons differentiated as they grew, meaning they separated into layers with rocky material sinking to form cores, while lighter ice floated upward to create icy mantles and crusts. The differentiation required heat to allow material to move, with heat sources, including the energy released by impacts during the accretion process, the decay of short-lived radioactive elements present when the solar system formed, and possibly some tidal heating if the early orbits were eccentric rather than circular. The inner 13 moons likely formed through similar processes, but either formed later from leftover disk material or represent fragments from larger parent moons that broke apart through collisions, or tidal disruption. The small sizes and close orbits suggest these moons occupy a zone where larger moons cannot easily survive due to tidal stresses and orbital perturbations. So either they formed small, or they represent remnants of larger bodies destroyed by impacts. The ongoing collisional evolution in the inner moon zone supports the idea that these moons are constantly being destroyed and reformed on timescales of hundreds of millions of years, creating a dynamic population rather than a stable configuration preserved since formation. The irregular moons, with their retrograde orbits and distant paths, clearly did not form from the circumplanetary disk and instead represent captured objects, as discussed previously. The capture process likely occurred during the first few 100 million years of solar system history, when planetary orbits were evolving and scattered populations of small bodies crossed the giant planets' orbital regions. Each captured irregular moon represents a successful outcome from thousands or millions of close encounters, where most objects either collided with the planet or escaped rather than achieving capture into stable orbits. One of the most important events in the Uranian system's history, possibly affecting both the planet and its moons, was the giant impact that tipped Uranus onto its side. The planet's 98-degree axial tilt, nearly perpendicular to its orbital plane, requires explanation beyond normal planetary formation processes, which tend to produce planets with relatively small tilts. The most widely accepted explanation invokes one or more massive collisions during the late stages of planet formation, where objects roughly the size of Earth or larger struck Uranus with enough momentum to knock it over. Such impacts would have been catastrophic, releasing energy equivalent to perhaps billions of nuclear weapons, and potentially disrupting the entire planetary system temporarily. If the major impact occurred after the regular satellites formed, the collision might have destroyed any pre-existing moons through the energy released, and the debris ejected, requiring the moons to form or reform from material orbiting after the impact settled. Alternatively, the impact might have occurred before the moons formed, with the circumplanetary disk that created the current satellites forming from debris thrown into orbit by the impact itself. This scenario, called the impact-generated disk hypothesis, suggests the impact created Uranus's current moon system, rather than destroying it, with the disk material gradually accreting into the moons we observe today. The hypothesis would explain why all the regular satellites orbit aligned with Uranus's current equator, despite the extreme tilt, because they formed from a disk that established itself aligned with the planet's post-impact rotation axis. The timing of Miranda's bizarre patchwork geology might also connect to the giant impact or its aftermath, though the connections remain speculative. If Miranda formed from the impact-generated disk, it might have accreted as a partially molten body that later froze and cracked, or it might have formed cold and then experienced heating from short-lived radioactive elements that created the coronae before the radioactivity decayed away. Alternatively, Miranda might have been shattered by a large impact of its own sometime after its formation, with the pieces reassembling in the jumbled configuration we observe, creating the Frankenstein moon from fragments that never quite fit together properly. The tidal evolution of the Uranian satellite system has played a major role in shaping the current orbital configuration. As tidal forces between Uranus and its moons caused the moons to gradually move outward over billions of years, while transferring rotational energy from the planet to the moons. This outward migration proceeds slowly, with the moons moving perhaps a few centimeters per year, but over billions of years, the accumulated motion amounts to substantial changes in orbital distances. The moons likely formed much closer to Uranus than they orbit today, and have gradually spiraled outward to their current positions through tidal evolution that continues at present. The tidal evolution also creates orbital resonances, where moons lock into configurations with orbital period ratios, forming simple fractions like 2:1 or 3:2. The resonances creating periodic alignments that enhance gravitational interactions between the moons. Resonances can pump orbital eccentricity through these periodic tugs, creating the elliptical orbits necessary for tidal heating to warm moon interiors through periodic flexing. Some of Uranus's moons may have passed through resonances in the past and experienced episodes of tidal heating that created the geological activity we observe in frozen form on surfaces, like aerials, with the resonances later breaking as continued tidal evolution changed orbital periods and destroyed the period ratios that created the resonances. The thermal history of each moon depended on its size, composition, orbital position, and whether it experienced tidal heating, creating the diverse range of geological outcomes we observe today. Large moons like Titania and Oberon retained internal heat longer than small moons like Miranda, simply due to their larger volumes and lower surface-to-volume ratios that reduced heat loss rates. Moons that experienced tidal heating episodes, possibly including Miranda and Ariel, would have remained warm longer and maintained geological activity extending later into their histories. Moons that never experienced tidal heating and formed small, like Umbriel possibly, would have cooled quickly and frozen geologically early, preserving ancient surfaces that record billions of years of bombardment. The current state of the system reflects billions of years of evolution from the initial formation through impact disruptions. Tidal migration, possible resonances and heating episodes, and gradual cooling into the frozen configuration we observe today. Each moon tells part of the story through its geology, with Miranda's patchwork suggesting disruption, and reassembly or intense tidal heating, Ariel's canyons and smooth plains indicating substantial internal melting, and cryovolcanism. Umbriel's dark, ancient terrain suggesting early freezing without significant later activity, and Titania and Oberon's large sizes allowing extended thermal evolution that created their distinct characteristics. The inner moons continue their dynamic evolution through ongoing collisions, while the irregular moons orbit unchanged since their capture billions of years ago, and together, the three populations create the complex satellite system we observe today. The most distinctive characteristic of the Uranian satellite system, the feature that makes it unique among all planetary moon systems in the solar system, is the extreme tilt that places the planet's equator and the regular satellite orbital planes nearly perpendicular to the planet's orbital plane around the Sun. Uranus's axial tilt measures 98 degrees, meaning the rotation axis points only 8 degrees away from lying completely in the orbital plane, creating the sideways planet configuration where the poles alternately point nearly toward or away from the Sun as Uranus orbits. This extreme tilt creates consequences for everything in the Uranian system, including all the moons that orbit aligned with the planet's equator, rather than with the solar system's general plane. The visual result when viewing the Uranian system from Earth or from space is that the entire moon system appears to orbit vertically rather than horizontally, with moons moving up and down relative to the planet rather than side to side as we observe with other planets' moons. During the periods when one of Uranus's poles points toward Earth, the moon's orbits appear as concentric circles or ellipses around the planet, the full system visible at once, like a target with Uranus at the center and the moons orbiting around it. During the periods when Earth views Uranus from its equatorial plane, the moons appear to move up and down past the planet. Their orbits edge on and creating a configuration where moons periodically pass in front of or behind the planet from our viewpoint. The rings share the same configuration as the moons, orbiting in Uranus's equatorial plane and therefore appearing vertical when viewed from most directions. The ring system, discovered through stellar occultations in 1977 and later imaged in detail by Voyager 2, consists of narrow dark rings, very different from Saturn's broad, bright ring system. The vertical orientation of the rings creates the unique appearance of a planet surrounded by a ring system, standing up like a Ferris wheel rather than lying flat like Saturn's rings. And the moons orbit within this vertical configuration, weaving among the rings or orbiting beyond them depending on their specific distances from the planet. The extreme seasonal variations resulting from the tilt affect every moon in the system. As the moons orbit with Uranus around the Sun on the planet's 84-year orbital period and experience the changing solar illumination that comes with that orbit. During Uranian summer at one pole, that pole and its surrounding hemisphere receive continuous sunlight for 42 Earth years, the equivalent of the planet's spring and summer combined, while the opposite pole experiences continuous darkness for that same 42-year period. The moons orbiting around these poles, therefore, spend decades in continuous illumination, followed by decades in continuous darkness, as they circle the planet through its extreme seasons. The transition periods at equinox create situations where the sun shines on Uranus's equator and where day-night cycles become more normal, with the moons experiencing roughly 12-hour day-night cycles as Uranus rotates every 17 hours and the moons orbit through the sunlit and shadowed sides of the planet. These equinox periods last only a few years out of each 84-year orbital period, representing brief transitions between the long periods of continuous daylight or darkness that characterize most of a Uranian year. The next Uranus equinox occurs in 2029, creating renewed interest in observing how the seasons change as the planet transitions from the northern summer that has persisted since the 1980s into the northern autumn and winter that will follow. The discovery of Uranus's extreme tilt came from telescopic observations revealing the planet's rotation axis orientation, with observers realizing that Uranus rotated in a completely different direction from all other planets. The cause of such extreme tilt remained mysterious for centuries, with theories ranging from the planet forming that way to ideas about gradual precession moving the axis over billions of years. But the currently accepted explanation involves one or more giant impacts that knocked the planet over during its formation. The impact hypothesis explains the tilt naturally, while avoiding the problems with other theories that struggle to produce such extreme axial tilting through gentler processes. The magnetic field of Uranus adds another layer of complexity to the sideways system, as the field is tilted 59 degrees from the rotation axis and offset from the planet's center, creating a highly asymmetric magnetosphere unlike anything around other planets. The offset and tilt mean that the magnetic poles lie far from the rotational poles, creating situations where the magnetic field strength varies dramatically at different locations around the planet, and where the moons experience very different magnetic environments depending on where they orbit. The magnetosphere also wobbles as Uranus rotates, the tilted offset field creating a corkscrew pattern as it sweeps around with the planet's 17-hour rotation period. The radiation environment around Uranus varies with position in this complex magnetic field, affecting the moons differently depending on their orbital distances and positions relative to the field geometry. The regular satellites orbit close enough to experience significant radiation from charged particles trapped in the magnetosphere, with the radiation contributing to the darkening and chemical processing of surface ices that creates the dark materials we observe on some moons. Miranda, orbiting closest, experiences the most intense radiation, while the irregular moons orbiting millions of kilometers from the planet experience negligible magnetospheric radiation and instead face primarily solar radiation and cosmic rays. Viewing the Uranian system from inside it, from any of the major moon's surfaces, creates perspectives on the sideways configuration that differ from the external view we get from Earth. From Miranda's surface during southern summer, the sun would circle around the sky at a nearly constant elevation, neither rising nor setting in the conventional sense, but instead spiraling slowly around the horizon over a 17-hour period as Uranus rotates and Miranda's tidal lock maintains one hemisphere facing. The planet, the sun's elevation would change only over decades as Uranus's orbit carried it around the sun and the seasons progressed, with the continuous daylight gradually giving way to twilight and eventually to continuous darkness as southern winter approached. The experience of seasons on the moons creates rhythms utterly unlike anything on Earth, where the 42-year periods of continuous light or darkness exceed human lifetimes, and where the transitions between seasons occur so gradually that daily changes remain imperceptible. Life adapted to such seasonal rhythms would need to handle decades of constant illumination followed by decades of darkness, creating biological challenges unlike anything terrestrial life faces, with its annual seasonal cycles and daily day-night rhythms. Whether life could exist in such an environment remains unknown, but the extreme conditions would certainly require adaptations very different from Earth organisms. The sideways configuration also affects how we observe the Uranian system from Earth, with the viewing geometry changing as Earth and Uranus orbit the Sun, and as Uranus's poles rotate through their 84-year cycle. During some periods, we see the system nearly pole-on, viewing all the moons and rings from above or below, and seeing their orbits as circles or ellipses. During other periods, we see the system edge-on, viewing it from the equatorial plane, and seeing the moons and rings as lines extending above and below the planet. The changing geometry creates different observing opportunities and challenges, with pole-on views allowing better separation of individual moons, while edge-on views create situations where moons occult and transit each other frequently. And so the sideways system continues its orbit around the Sun, carrying its family of 28 moons through space in a configuration unique in the solar system. The vertical ring system and moon orbits created by a tilt that resulted from a catastrophic impact billions of years ago. The orientation seems bizarre from our Earth perspective, but for anything existing within the Uranian system, the configuration would represent normality, the only arrangement they would know. With our own solar system's more typical planetary tilts seeming just as strange to Uranian observers as their sideways world seems to us. The transformation of the Uranian system from a barely known distant planet with 5 moons to a detailed world with a complex satellite and ring system occurred during a single brief encounter on 24 January 1986. The Voyager 2 spacecraft, launched in 1977 to take advantage of a rare alignment of the outer planets, arrived at Uranus after successful flybys of Jupiter in 1979 and Saturn in 1981, becoming the only spacecraft to visit the ice giant and its moon system. The encounter lasted only a few hours at closest approach, with the spacecraft racing past at tens of thousands of kilometers per hour. But during that brief window, Voyager revolutionized our understanding of Uranus and revealed an entire system we had barely glimpsed before. The approach to Uranus began months before closest encounter, with long-range imaging gradually resolving the planet from a featureless blue-green dot into a disk showing subtle atmospheric features. The moons appeared first as points of light, then as crescents showing increasing detail as the spacecraft closed the distance, with the imaging team carefully planning which moons to target and when, based on lighting conditions and spacecraft trajectory. The challenge of imaging at Uranus exceeded difficulties at Jupiter and Saturn, because the weak sunlight, at nearly 3 billion kilometers from the Sun, required long camera exposures, creating risks of blur from spacecraft motion that the team had to minimize through careful planning and spacecraft stabilization. Miranda became a priority target because it would pass closest to the spacecraft's trajectory, allowing the highest resolution imaging of any Uranian moon, though no one expected the bizarre patchwork terrain that the images would reveal. The first detailed images showing Miranda's surface came as a complete surprise to the science team, with the grooved coronae and the heavily cratered ancient terrain appearing to contradict each other, creating a moon that looked like it had been assembled from pieces of different worlds. The discovery of Verona Rupes, the tallest cliff in the solar system, added to Miranda's mystique and raised immediate questions about what processes could create such dramatic topography on such a small moon. The other major moons received less detailed coverage due to their greater distances from Voyager's trajectory, but each one revealed enough detail to show its distinct character. Ariel's bright surface and canyon systems appeared clearly in the images, confirming spectroscopic hints of fresh ice and revealing the cryovolcanic features that indicate past geological activity. Umbriel's dark surface and lack of obvious features, other than the mysterious bright ring in Wonder Crater, raised questions that remain unanswered decades later. Titania and Oberon showed their respective characters through crater densities and the presence or absence of obvious tectonic features, with Titania's Great Canyons visible and Oberon's mountain appearing near the terminator, where shadows emphasized its height. The discovery of 10 new moons during the Voyager encounter, adding to the 5 major satellites known from centuries of ground-based observation, revealed the inner moon system that had been completely invisible from Earth. The small dark moons appeared in images, carefully timed to look for objects among the rings and in the zone between the rings and Miranda, with computer processing enhancing the faint objects against the bright background of Uranus or the dark background of space. Each discovery required confirmation through detection in multiple images, ruling out cosmic ray hits or image artifacts and establishing orbital motion that confirmed the objects orbited Uranus rather than being background stars. The ring system received detailed study during the encounter, confirming the narrow rings detected from Earth through stellar occultations and revealing additional rings and ring structure invisible from Earth. The rings appeared dark and narrow, very different from Saturn's bright, broad ring system, consisting of material darkened by radiation and possibly organic compounds. The discovery of the shepherd moons Cordelia and Ophelia provided explanation for how the epsilon ring maintains its narrow width, despite perturbations that should cause rings to spread over time. Validating shepherd moon theories developed to explain Saturn's F-ring. The Uranus atmosphere itself became a subject of intense study during the brief encounter, with instruments measuring temperature profiles, wind speeds, atmospheric composition, and the complex tilted offset magnetic field that distinguished Uranus from all other planets. The featureless appearance of the atmosphere disappointed hopes for dramatic storm systems like Jupiter's Great Red Spot, but careful image processing revealed subtle bands and features that indicated wind systems and atmospheric circulation, despite the bland visual appearance. The measurements of atmospheric helium abundance, methane concentration, and temperature structure provided data that continues to inform atmospheric models decades later. The data transmission from Uranus back to Earth took nearly 3 hours. The radio signals traveling at light speed across the 2.7 billion kilometer distance from the spacecraft to Earth-based receiving stations. The distance created challenges for spacecraft operations because commands from Earth took nearly 3 hours to reach Voyager, and responses took another 3 hours to return, making real-time control impossible and requiring extensive pre-programming of the encounter sequence. The spacecraft executed its observation plan autonomously, following stored commands while periodically reporting status and beginning to transmit the precious images and measurements that would transform our understanding of the Uranian system. The months after the encounter brought continued data transmission. As Voyager sent back the hundreds of images and the streams of measurements from various instruments, with each data transmission carefully scheduled to maximize the science return from the limited bandwidth available at interplanetary distances. The imaging team processed images as they arrived, revealing new details and new discoveries with each transmission, while other science teams analyzed their instrument data to determine atmospheric properties, magnetic field characteristics, and other aspects of the Uranian system. The analysis continues to this day, with scientists still publishing new findings from Voyager data nearly 40 years after the encounter, as new processing techniques and theoretical understanding allow extraction of information that earlier analysis missed. The public reaction to the Voyager encounter images focused particularly on Miranda's bizarre terrain, with media coverage emphasizing the Frankenstein moon and the tallest cliff in the solar system, creating widespread fascination with this small world at the edge of the solar system. The coverage brought Uranus and its moons into public consciousness in ways that routine astronomical observations never could, transforming them from abstract astronomical objects into real places with strange landscapes and interesting stories. The legacy of that public engagement continues as educators and science communicators still use Voyager images to illustrate planetary science concepts and to inspire interest in solar system exploration. The limitation to a single flyby means that each moon was photographed from only one viewing geometry with one set of lighting conditions, leaving entire hemispheres unmapped and preventing the global coverage that orbital missions achieve. The Voyager images show roughly half of each major moon, the hemisphere that faced the spacecraft during the brief encounter, while the far hemispheres remain mysterious and unexplored, except for very low-resolution imaging that reveals almost no detail. The unmapped hemispheres could hold surprises as dramatic as Miranda's patchwork terrain, or they could prove similar to the imaged hemispheres. But without return missions, we cannot know what features await discovery on those unseen faces. The scientific legacy of Voyager 2's Uranus encounter extends far beyond the immediate discoveries, establishing baseline data against which future observations can compare to detect changes in the atmosphere, measuring physical properties like sizes and masses that ground-based observations cannot determine precisely, and revealing enough about each moon's surface and history to inform theories about satellite formation and evolution that apply throughout the solar system. The mission demonstrated that even brief flybys can revolutionize understanding. When spacecraft carry sophisticated instruments to bodies previously studied only from Earth, validating the approach of reconnaissance missions that survey targets quickly before later orbital missions return for detailed study. And so the Voyager encounter remains unique nearly 4 decades after it occurred. The only close-up study of Uranus and its moons, the source of essentially all our detailed knowledge about these distant worlds. The spacecraft continued beyond Uranus to encounter Neptune in 1989 before heading into interstellar space, where it continues to send data from beyond the solar system's edge. But for the Uranian system, Voyager's brief visit represents both the beginning of detailed knowledge and the current state of exploration. With no missions returning since, and no firm plans for future missions, despite the obvious scientific value such missions would provide. Placing the Uranian moon system in context requires comparing it to the satellite systems of other giant planets, examining how Uranus's moons resemble and differ from the moons of Jupiter, Saturn, and Neptune. The comparison reveals both common patterns that appear across all giant planet-moon systems and unique characteristics that distinguish Uranus's satellites from their counterparts elsewhere. The contrasts and similarities together inform our understanding of how satellite systems form and evolve, showing which processes operate universally and which depend on specific local conditions or historical accidents. Jupiter's satellite system, dominated by the 4 Galilean moons, dwarfs the Uranian system in terms of individual moon sizes and total satellite mass. Ganymede, Jupiter's largest moon and the largest moon in the entire solar system, exceeds the diameter of the planet Mercury and contains more than twice the mass of all Uranian moons combined. The other Galilean moons, Europa, Io, and Callisto, all exceed the size of any Uranian satellite, with even the smallest Galilean moon, Europa, measuring larger than Titania. The size difference reflects Jupiter's much greater mass, creating a deeper gravitational well that captured more material and allowed formation of larger satellites from the circumplanetary disk. The geological activity visible on Jupiter's moons also exceeds anything seen at Uranus, with Io's intense volcanism representing the most geologically active body in the solar system, and Europa's relatively young surface suggesting ongoing or recent activity. The extreme activity at Jupiter results primarily from tidal heating generated by orbital resonances among the Galilean moons, where the moons lock into configurations with period ratios that create periodic gravitational tugs, maintaining orbital eccentricities despite tidal circularization forces. Uranus's moons show far less activity, with only Miranda and Ariel displaying clear evidence of significant past geological processes, suggesting either that Uranian orbital resonances were weaker or that they occurred in the past and have since broken. Saturn's moon system presents a different comparison, with Titan dominating by mass, but the other major satellites showing sizes more comparable to Uranus's major moons. Titan, at 5,100 kilometers diameter, exceeds all Uranian moons dramatically and represents the only satellite in the solar system with a substantial atmosphere. But Saturn's mid-sized moons, like Rhea, Iapetus, Dione, and Tethys, fall into size ranges similar to Titania and Oberon. The surface appearances differ, with Saturn's moons generally showing brighter ice surfaces than Uranus's darker moons, possibly due to differences in radiation environment or due to ongoing resurfacing from cryovolcanism or from fresh material deposition that maintains brightness. The diversity of surface features on Saturn's moons exceeds what Voyager revealed at Uranus, with Enceladus showing active geysers erupting from the South Pole, Iapetus displaying its bizarre two-toned appearance with one hemisphere bright and one dark, Tethys showing the enormous Odysseus crater, and Mimas displaying the Death Star crater that nearly shattered the moon. Whether Uranus's moons harbor similar diverse features on their unmapped hemispheres remains unknown, but the limited coverage from Voyager prevents comprehensive comparison of the full diversity present in both systems. Neptune's satellite system differs fundamentally from Uranus's through the dominance of Triton, a moon larger than any Uranian satellite and containing more mass than all Uranus's moons combined. Triton's retrograde orbit indicates capture origin similar to the irregular satellites at Uranus, but on a much larger scale, with Triton possibly being a captured Kuiper Belt object or dwarf planet rather than a moon that formed in orbit around Neptune. The other Neptunian satellites are all small, comparable to Uranus's inner moons or smaller, creating a system with one giant captured moon and a collection of minor satellites rather than the more balanced distribution of major moons at Uranus. The naming conventions distinguish Uranus's moons from all other planetary satellites, with the Shakespearean and Pope literary tradition unique among the planets. Jupiter's moons take names from Zeus's lovers and descendants in Greek and Roman mythology, Saturn's from Greek and Roman mythology generally, and Neptune's from Greek and Roman sea deities and mythological water-related figures, while Uranus alone draws from English literature. The tradition began with the discovery of the first moons and has continued through all subsequent discoveries, creating a satellite system whose names evoke plays and poems rather than ancient myths. The synchronous rotation characteristic of all major moons at Uranus also appears universally among major satellites throughout the outer solar system. With tidal forces having locked rotation periods to orbital periods for essentially every large satellite close enough to its planet for tides to operate effectively. The inner small moons at Uranus probably also rotate synchronously, though their irregular shapes make the concept less well-defined than for the larger, roughly spherical moons. The irregular outer moons at Uranus may or may not be tidally locked, depending on their shapes and internal structures, but their great distances make tidal locking much slower, possibly requiring longer than the solar system's age to achieve synchronous states. The absence of a truly dominant large moon at Uranus distinguishes the system from Jupiter, Saturn, and Neptune, which each possess at least one satellite significantly larger than the others. Uranus's largest moons, Titania and Oberon, are comparable in size to each other, and only slightly larger than Ariel and Umbriel, creating a more balanced distribution where no single moon gravitationally dominates the system. This balance possibly reflects the total mass available in Uranus's circumplanetary disk during formation, with the disk containing enough material to create several moderate-sized moons, but not enough to form a truly giant satellite like Ganymede or Titan. The radiation environments differ between the Jovian and Saturnian systems and the Uranian system due to differences in magnetic field strengths and configurations, with Jupiter's intense magnetic field creating radiation belts that far exceed anything at Uranus, while Saturn's weaker field creates intermediate conditions. The radiation affects surface chemistry and colors differently depending on intensity and particle energies, possibly contributing to the darker average color of Uranian moons compared to the brighter appearance of many Saturnian satellites. The complex tilted offset magnetic field at Uranus creates unique radiation patterns not replicated at other planets, adding to the distinct character of the Uranian radiation environment. The total system mass provides another comparison point, with all of Uranus's moons together containing only about 0.04% of the planet's mass, a fraction smaller than the fractional mass of Jupiter's Galilean moons, or of Saturn's Titan, but larger than the fractional mass of Earth's moon. The relatively small total satellite mass at Uranus suggests either a less massive circumplanetary disk compared to Jupiter or Saturn, or possibly that some disk mass was lost before forming satellites or ejected by the giant impact that tipped Uranus over. The irregular satellites contribute negligibly to the total mass, as even the largest irregular moon, Sycorax, contains only a tiny fraction of Miranda's mass. The exploration history also differs dramatically, with Jupiter and Saturn both receiving multiple spacecraft encounters, including dedicated orbiter missions like Galileo at Jupiter and Cassini at Saturn, while Uranus has received only the single Voyager 2 flyby. The disparity in exploration coverage means our knowledge of Uranian moons comes from images covering roughly half the surface of each major moon during one brief encounter decades ago. The Jovian and Saturnian moons have been mapped comprehensively with multiple instruments over extended periods, revealing details impossible to discern from single flyby observations, and allowing scientists to study temporal changes and complex three-dimensional structures through careful repeated imaging. The similarities among all giant planet-moon systems provide insight into universal processes of satellite formation and evolution, regardless of specific planetary characteristics. All the systems show regular moons in prograde circular orbits close to their planets, formed from circumplanetary disks during or shortly after planetary formation. All possess irregular satellites in distant, eccentric, and often retrograde orbits, captured from heliocentric orbits through gravitational interactions during the chaotic early solar system. All show evidence of past geological activity, at least on some moons, indicating that internal heat sources operated early in satellite history, even if most moons are now geologically dead. The differences reflect the specific circumstances of each planetary system, including planetary mass affecting disk mass and satellite sizes, distance from the Sun affecting ice and rock ratios, and volatile compositions impact history, creating unique cratering patterns and possibly catastrophic disruptions, and magnetic field properties affecting radiation processing of surfaces. Uranus's extreme axial tilt stands as the most distinctive characteristic, creating the sideways system orientation unique among all planetary moon families, and producing seasonal variations in illumination and solar heating, unlike anything the other giant planet satellites experience. The Uranian moon system occupies a middle ground in many characteristics, neither as massive and active as the Jovian system, nor as dominated by a single giant moon as the Neptunian system, neither as bright as many Saturnian moons, nor as thoroughly explored as any of them. This intermediate position makes Uranus valuable for understanding how satellite systems vary across the parameter space available to giant planets, filling in the gaps between the extremes represented by Jupiter and Neptune. The unique tilt adds a dimension of variation not available elsewhere, making the Uranian system the only place to study how extreme seasonal forcing affects moon surfaces and potential subsurface processes. The literary names create a poetic atmosphere around the Uranian moons that distinguishes them culturally from other planetary satellites, evoking stories and characters rather than gods and mythological figures. Miranda and Ariel and Umbriel carry associations from Shakespeare's plays and from Alexander Pope's poetry, connecting these distant ice worlds to human imagination and literary tradition in ways that Zeus's lovers or sea gods do not. The tradition continues with new discoveries, as astronomers naming newly found Uranian satellites continue to select names from the works of Shakespeare and Pope, maintaining the unique character of this moon family. The orderly orbits of the regular Uranian moons resemble the regular satellite systems at Jupiter and Saturn in their circular prograde paths aligned with the planetary equator, demonstrating that the process of satellite formation from circumplanetary disks produces similar orbital configurations regardless of planetary tilt. The irregular moons similarly resemble irregular satellites elsewhere in their eccentric, inclined, and often retrograde orbits, showing that capture mechanisms operate similarly around all giant planets. The universality of these patterns across different planets with different characteristics reveals fundamental processes that operate throughout the solar system. The geological features visible on Uranian moons find parallels at other moons, even when the specific details differ, with canyons at Ariel resembling canyons on other icy satellites. impact craters appearing everywhere in similar size distributions and morphologies, and evidence of past tectonic activity showing similar fault structures and graben formations. These parallels indicate that ice and rock respond to forces and stress in consistent ways, regardless of which planet the Moon orbits, with the laws of physics and chemistry producing similar outcomes from similar conditions. Where Uranian moons show unique features, like Miranda's extreme cliffs, the differences likely reflect unique events or conditions specific to that moon's history, rather than fundamentally different physical processes. The future, comparative planetology, will benefit enormously from eventual missions returning detailed data from Uranus's moons, allowing direct comparison of surface compositions, internal structures, and geological histories with the well-characterized moons at Jupiter and Saturn. The comparisons will help isolate which differences arise from formation conditions, which from subsequent evolution, and which from random chance or unique catastrophic events. Understanding the Uranian moons in the context of all satellite systems enriches our comprehension of each individual system and of the processes that create and shape moons throughout the solar system and, potentially, around exoplanets orbiting distant stars. The future of Uranian moon exploration holds promise for transforming our limited knowledge into comprehensive understanding, comparable to what decades of missions have achieved at Jupiter and Saturn. The gap in exploration, with nearly 4 decades passing since Voyager 2's brief flyby and no confirmed missions currently en route, reflects the practical challenges of reaching Uranus and the competition for limited planetary science funding, rather than any lack of scientific interest. Multiple proposals for Uranus missions have been developed and studied over the years, with mission concepts ranging from modest flybys to ambitious orbiters with atmospheric probes and landers, each offering different levels of scientific return, balanced against different costs and technical requirements. The distance to Uranus creates the primary challenge for mission design, as the planet orbits at 19 astronomical units from the Sun, requiring spacecraft to travel nearly 3 billion kilometers to reach their destination. Current propulsion technology using chemical rockets and gravity assists from inner planets typically requires 10 to 15 years of flight time to reach Uranus, creating long mission durations that span careers and challenge spacecraft reliability. Advanced propulsion concepts, including nuclear electric propulsion or solar electric propulsion, could potentially reduce flight times to 7 or 8 years. But these technologies require development and testing before implementation on outer planet missions. The low solar intensity at Uranus's distance makes solar panels impractical for power generation, requiring missions to use radioisotope thermoelectric generators that convert heat from radioactive decay into electricity. The limited supply of plutonium-238 used in these generators creates a practical constraint on outer solar system missions, with available material carefully allocated among competing mission proposals and future production uncertain. The power available from RTGs also decreases over time as the plutonium decays, requiring mission designs to account for declining power budgets over the extended mission duration, including the 10-plus-year cruise to Uranus. The current leading mission concept, studied extensively by NASA as part of planetary science, decadal surveys envisions an orbiter arriving at Uranus and spending several years systematically studying the planet, its rings, its magnetosphere, and its satellite system. The orbiter would carry a suite of scientific instruments, including cameras for imaging surfaces in visible and infrared wavelengths, spectrometers for measuring surface and atmospheric compositions, magnetometers and plasma instruments for characterizing the magnetic field and charged particle environment, and radio science equipment for measuring gravitational fields and probing atmospheric structure. An atmospheric probe might deploy during orbit insertion, descending through the Uranian atmosphere while measuring composition, temperature, pressure, and winds before being crushed by increasing pressure at depth. The orbital tour would visit each major moon multiple times through carefully designed flybys that use gravitational assists from the moons to reshape the orbit and enable encounters with different satellites. The tour design represents a complex optimization problem, balancing the desire to visit all moons with the constraints of orbital mechanics and propellant limitations, with each flyby chosen to maximize scientific return while enabling subsequent encounters. Close flybys of Miranda would prioritize high-resolution imaging of the bizarre patchwork terrain and the towering cliffs, attempting to understand the geological history that created such extreme features on such a small moon. Aerial flybys would focus on the canyon systems and smooth plains, searching for evidence of past cryovolcanism and studying the tectonic features that suggest the moon expanded as its interior evolved. High-resolution imaging could reveal details of the valley floors and wall structures invisible in Voyager's images, while spectroscopy could map compositional variations that might indicate different ice types or contamination by rocky material. Gravity measurements during close flybys could constrain internal structure, revealing whether Ariel possesses a differentiated interior with a rocky core and ice mantle, or remains a mixed ice rock body. The dark surface of Umbriel would receive special attention during dedicated flybys, with instruments attempting to determine what makes this moon so much darker than similar-sized Ariel, and why it shows so little geological activity. Spectroscopy could identify the dark material coating the surface, testing whether it consists of carbon-rich compounds, radiation-processed organics, or some other darkening agent. The mysterious bright ring, Wonder, would be imaged at high resolution to determine its composition and origin, possibly revealing fresh ice exposed by a relatively recent impact, or an unusual composition that resists the darkening affecting the rest of the surface. Titania and Oberon would receive multiple flybys to map their surfaces comprehensively and study their geological histories in detail, with particular attention to Titania's Great Canyon systems and Oberon's ancient, heavily cratered surface. The comparison between these two similar-sized moons could reveal why Titania shows more evidence of geological activity and what factors controlled the evolution of each. Gravity measurements and topographic mapping would constrain internal structures and surface deformation patterns, testing whether either moon retains internal heat or whether both have frozen completely solid. The inner moons, visible only as tiny dots in Voyager images, would benefit enormously from close-up imaging revealing their shapes, surface features, and relationships with the ring system. High-resolution images of the shepherd moons Cordelia and Ophelia would show how these small moons interact with ring particles, while images of Puck and the other inner satellites would reveal impact histories and possible collisional evolution. The discovery of additional small moons orbiting among the known satellites would not surprise anyone, as improved imaging from an orbiter would detect objects too small or too faint for Voyager to see. The irregular outer moons present greater challenges for close study due to their immense distances from Uranus, but even distant imaging would provide valuable data on their sizes, shapes, colors, and rotation states. Spectroscopic observations could determine compositions and compare the irregular satellites to Kuiper belt objects and to irregular moons orbiting other giant planets, testing capture scenarios and constraining the dynamical history of the outer Uranian system. The outer moons might receive dedicated flybys late in the mission if propellant budgets allow, providing close-up views of these captured visitors from the outer solar system. The search for subsurface oceans would represent a high priority for moon studies, using multiple techniques to detect liquid water layers beneath icy crusts. Gravity measurements during close flybys could reveal mass distributions inconsistent with purely solid interiors, while magnetic induction signatures might indicate electrically conductive liquid layers responding to Uranus's time-varying magnetic field. Surface features, including patterns of cracks and ridges, could provide indirect evidence for subsurface oceans if they match patterns expected from tidal flexing of ice shells floating on liquid layers. The atmospheric probe, deployed during arrival, would provide our first direct measurements of Uranus's atmospheric composition below the cloud tops, measuring abundances of hydrogen, helium, methane, ammonia, water, and other constituents as the probe descends. The measurements would constrain planetary formation models and reveal whether the Uranian atmosphere differs significantly from the Jovian and Saturnian atmospheres in ways that reflect ice giant formation or evolution. The probe data would also characterize the temperature and pressure structure, measure wind speeds at different depths, and possibly detect lightning or other atmospheric phenomena before the probe succumbs to crushing pressure. The rings would receive systematic study through imaging at multiple wavelengths and phase angles, revealing particle size distributions and compositional variations invisible in Voyager's images. Occultation observations, where the spacecraft watches stars pass behind the rings, would measure ring structure at very high resolution and detect features too small to image directly. The relationships between rings and moons would be studied in detail, testing theories of ring confinement and evolution and searching for embedded moonlets or other structures within the rings. The planetary magnetic field and magnetosphere would be mapped comprehensively through measurements at many locations during the orbital tour, characterizing the strange tilted offset dipole field and understanding how it creates unusual radiation belt and auroral patterns. The interaction between the magnetosphere and the solar wind would be monitored continuously, revealing how this unique magnetic configuration responds to varying solar wind conditions. The magnetic field measurements would also constrain interior structure by revealing how deep the dynamo region extends and what materials must be present to generate the observed field. The timeline for such a mission realistically points toward launch in the late 2020s or early 2030s, if approved and funded in the current decade, with arrival at Uranus in the late 2030s or early 2040s, depending on the specific launch year, and trajectory. The long timescales reflect the realities of mission development, spacecraft construction, and flight time, with mission planners working now on missions that will reach their targets decades in the future. Scientists and engineers currently in graduate school or early in their careers might lead the analysis of data from future Uranus missions, continuing work begun by their professors and advisors decades earlier. The scientific community strongly supports a Uranus mission, with the most recent Planetary Science Decadal Survey identifying a Uranus orbiter and probe as the highest priority flagship mission for the coming decade. The recommendation reflects both the significant scientific questions a Uranus mission would address and the recognition that the ice giants remain the least explored class of planets in our solar system. The endorsement increases the likelihood of eventual mission approval, though budget constraints and competing priorities mean that approval remains uncertain until formal decisions are made. International collaboration might enable a more ambitious mission than any single space agency could mount independently, with NASA potentially partnering with the European Space Agency or other partners to share costs and expertise. International missions bring political and coordination challenges, but also allow pooling of resources and capabilities that enhance scientific return. The success of international collaborations like Cassini-Huygens at Saturn demonstrates that multi-agency missions can achieve remarkable results despite added complexity. The decades until a Uranus mission arrives allow time for ground-based and Earth orbital observations to continue refining our knowledge and identifying specific questions for spacecraft instruments to address. The James Webb Space Telescope and future giant ground-based telescopes will observe Uranus and its moons at wavelengths and resolutions impossible before, potentially detecting atmospheric changes, surface variations, or other phenomena that guide mission planning. These observations bridge the gap between Voyager's fleeting glimpse and future comprehensive exploration, slowly building understanding while we wait for spacecraft to return. We return now to where we began, looking outward from Earth, toward the pale blue dot of Uranus, orbiting in the cold outer solar system, with its family of 28 moons. The journey through this satellite system has taken us from Miranda's impossible cliffs, through Ariel's bright canyons and Umbriel's ancient darkness, to the paired giants Titania and Oberon, then among the crowded inner moons and the distant captured irregulars. Each world revealed its own character through ice and rock shaped by billions of years of gravity and impacts, an internal evolution, creating a family of moons as diverse as any planetary system. Miranda remains the most dramatic, its surface fractured into the patchwork terrain that gave it the Frankenstein nickname, and the towering Verona Rupes that stands as the tallest cliff in the known solar system. The image of that 20-kilometer vertical drop persists in memory. A wall of ice so tall that jumping from the top would mean falling for 12 full minutes before landing gently at the bottom in the weak gravity. The coronae, with their parallel grooves and the sharp boundaries between different terrain types, continue to puzzle scientists, raising questions about what forces could create such features on such a small moon, and whether Miranda was shattered and reassembled, or merely heated and deformed. Ariel's brightness and its network of canyons create a different impression, showing a moon that experienced significant geological activity in its past. and renewed at least portions of its surface. The sinuous valleys, suggesting cryovolcanic flows, and the tectonic graben, indicating crustal extension, demonstrate that even these cold, distant moons possess enough internal heat to drive geological processes. For some portion of their histories, the relatively fresh surface with fewer craters than Umbriel or the outer moons tells us that Ariel's activity continued later than on most Uranian satellites, possibly extending to within the last few 100 million years. Umbriel's darkness and uniformity present the opposite picture. A heavily cratered ancient surface showing minimal signs of geological modification since the late heavy bombardment ended billions of years ago. The dark coating that makes Umbriel the darkest major Uranian moon might consist of carbon compounds or radiation-processed organics, but its exact composition remains unknown, pending future spectroscopic measurements. The bright ring Wunder stands as the one anomaly on this otherwise uniform surface, a mystery whose solution awaits higher resolution images and compositional data than Voyager provided. The giant pair, Titania and Oberon, dominate the outer moon system by size and mass, each roughly 1,500 kilometers in diameter, and containing ice rock interiors that might still retain some internal heat. Titania's Great Canyon systems demonstrate past tectonic activity, possibly driven by expansion as the interior froze and increased in volume, while Oberon's heavily cratered surface and the mysterious dark patches on crater floors hint at ancient impact events or possible cryovolcanic eruptions. These two moons anchor the outer reaches of the regular satellite system, orbiting far enough from Uranus that their orbital periods measure in Earth days rather than hours. The 13 inner moons crowd together between the rings and Miranda, in a zone where orbital crowding creates an unstable environment where collisions must occur periodically. These small, irregular bodies act as shepherds for some of the rings, while themselves experiencing a collisional evolution that grinds them down and occasionally destroys and reforms them through accretion of fragments. Puck stands out as the largest, massive enough to pull itself into a roughly spherical shape, while the others remain irregular, lumpy bodies, shaped more by impacts than by gravity. The 10 irregular moons, orbiting in the distant outer reaches, tell a different story of capture rather than formation, their retrograde orbits and high eccentricities marking them as visitors from elsewhere in the solar system. Sycorax and Caliban and their companions originated somewhere in the outer solar system and fell into Uranus's gravitational grasp during the chaotic early period when planets were still migrating and objects still flew freely through interplanetary space. These small dark bodies contribute little to the total system mass, but add diversity to the Moon family and provide evidence of the capture processes that operated throughout the outer solar system. The sideways orientation of the entire system remains its most distinctive characteristic, with all the regular moons orbiting in the equatorial plane tilted 98 degrees from vertical. This configuration creates the vertical appearance of moon orbits when viewed from Earth, and produces the extreme seasonal variations that cycle each pole through 42 years of continuous sunlight, followed by 42 years of continuous darkness. The moons experience these same extremes, with surface temperatures varying between the endless summer and the endless winter in patterns unlike anything occurring in normally oriented planetary systems. The literary names create a unique cultural identity for the Uranian moons, connecting these distant ice worlds to human storytelling and imagination through Shakespeare and Pope. Miranda and Ariel invoke the tempest. Umbriel recalls the rape of the lock. Titania and Oberon echo A Midsummer Night's Dream, while Cordelia and Ophelia and the others draw from the tragedies. The tradition distinguishes these moons from the mythologically named satellites orbiting other planets, creating an atmosphere of poetry and drama around worlds of frozen ice and ancient craters. The single Voyager 2 flyby in January 1986 provided all our close-up knowledge of these moons, a brief encounter that revolutionized understanding, but left half of each moon unmapped in the winter darkness. The images transmitted back to Earth revealed Miranda's bizarre terrain, Ariel's canyons, Umbriel's darkness, the cliffs and craters on Titania and Oberon, and the small inner moons invisible from Earth. Decades later, these images remain our best views of the Uranian satellites. Though Earth-based telescopes and the Hubble Space Telescope have added discoveries of new small moons and crude maps of surface color variations, the future holds possibilities for returning to this system with orbiters and probes that could study each moon systematically over several years. The scientific questions raised by Voyager's brief glimpse await answers from instruments that can image unmapped hemispheres, measure compositions spectroscopically, detect subsurface oceans through gravity and magnetic measurements, and observe how the moons change over time. A dedicated Uranus mission would transform our understanding as dramatically as Galileo and Cassini transformed our knowledge of the Jovian and Saturnian systems, revealing these ice worlds in the detail they deserve. Until such missions arrive, the 28 moons continue their ancient orbits, circling Uranus in the cold outer solar system, without regard for human observation or understanding. Miranda's cliffs stand untouched by wind or erosion, preserved in the airless vacuum for billions of years. Ariel's canyons remain frozen exactly as they appeared when cryovolcanic flows stopped and the surface froze solid hundreds of millions of years ago. Umbriel maintains its dark, uniform appearance, accumulating new impact craters at the slow rate characteristic of the outer solar system. Titania and Oberon trace their wide orbits, their ancient surfaces recording the bombardment history of the early solar system. The inner moons orbit rapidly through their crowded zone, occasionally colliding and shattering and reforming as they have done throughout the age of the solar system. The irregular moons follow their eccentric retrograde paths. Visitors from elsewhere, now permanently bound to Uranus by gravity. Their surfaces, possibly recording composition and structure from the region of the solar system where they originally formed. The rings, shepherded and confined by some of the inner moons, consist of countless particles, ranging from dust grains to boulders, all orbiting in the equatorial plane of the tilted planet. The system exists independent of our knowledge or attention, operating according to gravity and orbital mechanics and thermodynamics without requiring observation. The moons orbited before humans existed and will continue orbiting long after humanity has ended. Their motions determined by mathematics and physics that preceded life and will persist after life. Our understanding represents merely a recent and temporary awareness of patterns and processes that have operated for 4.5 billion years without anyone watching or caring or measuring. The knowledge we possess came from brief glimpses and careful measurement and theoretical reasoning, from Voyager's flyby and from ground-based telescopic observations, and from the mathematics of orbital mechanics and planetary formation. Each fact about these moons represents an achievement of human curiosity and ingenuity, transforming distant points of light into understood worlds with measured sizes and mapped surfaces and inferred compositions. The transformation from ignorance to knowledge proceeds slowly through patience and careful observation, each generation adding understanding that the next generation will build upon. The quiet beauty of these ice moons orbiting their sideways planet deserves appreciation beyond scientific interest, as the image of 28 worlds circling through the cold outer solar system carries aesthetic power independent of data and measurements. The pale blue planet, with its vertical ring system and its family of moons, creates a picture of cosmic architecture, shaped by gravity and chance into a configuration unlike anywhere else. The remoteness adds to the beauty, as these worlds pursue their orbits in near darkness far from the warming sun, existing in perpetual twilight, broken only by the reflected light from Uranus itself. The Shakespearean names resonate with meanings beyond their astronomical reference, connecting these frozen moons to human drama and emotion and storytelling. Miranda's name carries associations of wonder and innocence. From the Tempest, Ariel suggests the airy spirit. Umbriel invokes darker moods, while Titania and Oberon bring fairy magic and midsummer dreams. The associations enrich our sense of these worlds beyond their physical characteristics, adding layers of meaning that pure mythological names might not carry. The journey through this moon system reaches its natural end, having explored each major moon individually and understood the system as a whole. We have stood on Miranda's cliffs, flown over Ariel's canyons, observed Umbriel's darkness, visited the giants Titania and Oberon, and recognized the smaller moons, both inner and irregular. We have traced the history from formation through evolution to the present frozen state, understood the sideways orientation, learned of Voyager's discoveries, and contemplated future missions that might return to study these worlds in detail. The moons themselves continue unchanged by our attention, orbiting as they always have through the cold outer solar system. The knowledge we carry back from this imagined tour represents understanding built from decades of observations and analysis, facts assembled into a coherent picture of an ice moon system shaped by the same processes that created satellites throughout the outer solar system. The understanding will deepen with future observations and eventual spacecraft missions. But for now, we know these worlds well enough to appreciate both their beauty and their mystery. And so we leave the Uranian moons behind, returning across the vast distance to Earth with images of impossible cliffs and bright canyons and dark ancient surfaces and families of small moons orbiting in crowded zones. The 28 worlds continue their orbits, Miranda and Ariel and Umbriel and Titania and Oberon and Puck, and all the others, each one a place that exists independently of human awareness, each one orbiting through the darkness in the cold outer solar system, beneath the faint light of the distant sun, around the pale blue planet that rotates on its side. In a system unique among all the planetary families we know, waiting in the frozen silence for the next visitor to arrive and reveal the secrets still hidden in darkness on their unmapped hemispheres, continuing as they have for billions of years, continuing as they will for billions more, the 28 moons of Uranus orbiting through the eternal cold.